This is 2.7 VSEPR and bond hybridization. Our outcome is I can explain structural properties and electron properties of molecules using the relationship between Lewis diagrams, VSEPR theory, bond order, and bond polarity. So here we have a chart that shows the bond angle and electron domains for several molecules. So a bond angle is the angle made by three connected nuclei in a molecule. And by convention, we always report it as being between 0 and 180. So here we have several molecules. We're given the number of bonding domains and non-bonding domains, as well as a bond angle. So how is the number of bonding domains determined? It's the same as the number of bonding atoms. And the non-bonding domains is the same as the number of lone pairs on the atom. So roughly we see that we have bond angles grouped around 180, 120, and 109. And this is related to the total of bonding and non-bonding electron groups. So 2 groups gives us 180, 3 groups gives us 120, and 4 groups gives us 109. So a domain of electrons is going to tend to repel other domains of electrons. So those could be lone pairs or they could be bonding pairs. So domains of electron around a central atom are going to orient themselves to minimize the electron-electron repulsion between the domains. So 2 domains of electrons, we get an angle of 180, and that makes sense because that's the farthest those 2 can get away from each other. For 3 domains, we get 120. We get this trigonal planar shape. So the predicted bond angle for these molecules, again, just based on the total number of bonding and non-bonding pairs, 180 for carbon, 109 for oxygen and water, as well as in methane and ammonia. And then in our nitrate ion, it's going to be around 120. So the names for molecular shapes are based on the position of the atoms in the molecule, not the position of the domains. So for example, in a bent molecule, we could have angles close to 120 or 109, depending on what lone pairs are present. So bent molecules have 2 bonding domains around the central atom. So if there is 2 bonding domains and 1 non-bonding domain, we would expect bond angles around 120. If there's 2 bonding and 2 non-bonding, so a total of 4 domains, we expect to see angles close to 109. So in this molecule here, the central carbon is attached with a single and a triple bond. So that gives us 2 domains of electrons. And since there's no lone pairs, 2 domains, we have an angle of 180. In this molecule down here, the central nitrogen has a single bond, a double bond, and a lone pair. So that's 3 electron domains. So we expect a bond angle to be around 120. So here, this is para-aminobenzoic acid, which is used in sunscreens. And we just want to count the number of domains on each identified atom. And based on that number of domains, if it's 4, it's going to be 109. If it's 3, it's going to be 120. If it was 2, then it would be 180. So how can we predict the shape of a molecule from its Lewis structure? So that Lewis structure allows us to see how many bonding and non-bonding domains are present. So these domains are made from electrons which repel each other. So this will force the molecule into a 3D shape that minimizes those repulsions. So many chemists describe the way that electrons are arranged around an atom differently than what we've been describing it. So the electron pairs around the central atom is said to be in a set of orbitals that are hybridized from atomic orbitals for the atom. So there's this conversation going on between the orbitals in an atom. So if one s orbital and one p orbital are used, then we form two hybrid orbitals that are called sp hybrid. If we used one s and two p's, we would make a total of three orbitals that are called sp2 hybrid orbitals. So we can assign the hybridization based on the experimentally determined bond angle, which is, of course, related to the shape of the molecule. So here's methane. What is the predicted bond angle? So we would expect, since we have 4 domains, that our bond angle would be 109, roughly. And so that indicates to us that there's sp3 hybridization going on. So around that carbon, the s and 3p orbitals are interacting with each other, and this forms sp3 hybridization. So this is showing us that carbon is able to form 4 bonds, which is what we would predict with the Lewis structure. The Lewis structure of water is shown. What is the expected hybridization? So we have 4 domains, which means we're expecting bond angles around 109, and so we have sp3 hybridization. So here is one of the resonance structures for nitrate. What is the predicted bond angle? So for the nitrogen atom, there are 3 domains here: a single bond, another single bond, and a triple or a double bond. So this indicates to us bond angles of 120, which means that there must be sp2 hybridization going on. Looking at the bond angle in hydrogen peroxide, determine the hybridization. So whenever I draw my Lewis structure here, I have a total of 6 plus 6 is 12, 13, 14 electrons to work with here. So I end up with 4 electron domains on the oxygen. So there's a lone pair, and 2 bonding pairs. So we expect sp3 hybridization and a bond angle around 109 degrees. So sigma and pi bonds. So how are bonds formed from electron clouds? So overlapping electron clouds are able to interact with each other. A wave function is a big, complicated 3D math equation. So it's going to be in x, y, and z, 3 variables, that describes the location of electrons around an atom or molecule. And this is based on probability. If you solve this big, complicated 3D equation, you get a 3D shape, and that is giving you the shape of the electron clouds. So we have named these shapes S, P, D, and F. So in this little picture that I have here, I'm showing you a bunch of different orbitals. So our S orbital is just spherical. Our p orbital is split into 3 pieces, x, y, and z. And then we have the d and the f orbitals, which have all kinds of crazy geometries. So how do we form that hybridized sp3 orbital? And why do the electrons arrange themselves in this way? So the s and p orbitals are able to interact with each other. And the best way to minimize the electron-to-electron repulsions would be to form 4 identical hybridized sp3 orbitals. So if you think about something like carbon, which has an electron configuration of 1s2, 2s2, 2p2. So based on this electron configuration, we might predict that carbon can only form 2 bonds here, because in that s orbital, those electrons are already paired. But what happens is these s and p orbitals combine together to form sp3 orbitals, allowing carbon to make 4 bonds instead of the 2 that we might predict from the electron configuration. Why do the balloons naturally form the tetrahedral shape? How does this relate to the shape of a molecule? So the balloons can't occupy the same space, so they're forced into that tetrahedral shape. So carbon has this tetrahedral shape as the result of sp3 hybridization, allowing it to form those 4 bonds. So the electron clouds also cannot occupy the same space. They repel each other, so they're forced into a tetrahedral shape. Water is a bent molecule because those 4 domains want to get as far apart as possible. So the s orbital on both hydrogens overlaps with one of the sp3 orbitals on oxygen. So those sp3 orbitals are forced into that tetrahedral shape. So no matter where you place those 2 hydrogens, you're stuck in that same shape. This gives water that bent shape. So this shape, along with the differing electronegativity values of hydrogen and oxygen, are what make water polar. If water was a linear molecule, like you might predict based on the Lewis structure alone, then we wouldn't have the polarity. It would be a bit like carbon dioxide, where the positive and negative charges, the partial charges, just end up adding up to 0. So the formation of a sigma bond. So a sigma bond is formed whenever 2 hybridized sp2 orbitals interact, and this forms a single carbon-to-carbon bond. A pi bond is a double bond. So it is formed whenever 2 unhybridized p orbitals interact, and this allows the formation of a double bond. So for your reflection questions, why do we need both Lewis and VSEPR to predict the properties of molecules? This is because we need to know both how the electrons are arranged amongst atoms and also what the 3D shape of the molecule is. So bonds are formed from the overlap between atomic orbitals, sp, d, and f. When you overlap an s with 3p orbitals, you get that sp3 hybridization, allowing things like carbon to form 4 bonds total.